Our next speaker is Eric Culver from
University of Colorado, Denver.
There it is. Okay. So Eric from University of Colorado, Denver, and he'll be speaking about applying the potential method to the edgeless coloring conjecture. So take it away.
Cool. Thank you, everyone, for coming. Let's talk about what the edgeless coloring conjecture is to start with. So we are talking about edge coloring a graph. So if you have a graph, a proper edge coloring, usually the word proper gets dropped there, it's implied, is when you assign colors to the edges of a graph such that edges that are incident, that touch one another at one of their endpoints, are given different colors. And so there is a graph here on the screen, and I can color the edges using these four colors to give it a proper edge coloring. And so since this uses four colors, it is 4 edge colorable. If I used 5, I'd say 5 edge colorable. And then the edge chromatic number of a graph is the minimum K such that the graph is K edge colorable. So for this particular graph, its edge chromatic number is 4. We know it's at most 4 because it's 4 edge colorable, but just believe me, you can't do it with 3 or 2 or anything like that. So for this particular graph, its edge chromatic number is 4. Which this is lower bounded by the maximum degree of the graph. That's what that delta of G is referring to, which is just looking at all the vertices, which vertex has the most edges incident to it. The number of those edges is the max degree. The edge list coloring is sort of a generalization of just edge coloring. So an edge list assignment is you assign lists of colors to each of the edges. And what you want is they're essentially limiting what colors can be given to a particular edge. When we were just edge coloring, we could have put any color we wanted on an edge. But with this list assignment, we're limiting what colors can go on each edge. And the size of a list assignment is the size of the smallest list. So in the example list assignment, all the lists are of size 3. So the size of the list assignment is 3. If we have a particular list assignment L, then the graph is L colorable if we can give the graph a proper coloring where the colors are picked from those lists, those restrictions. And so this particular graph with this particular list assignment is colorable. If you look at this picture for a little bit, you can see that all of these colors have been chosen from the list for that edge, and the coloring is proper. And we say that a graph is K edge choosable if it's L colorable under any edge list assignment of size at least K. And this is kind of hard to check because there's lots of different edge list assignments that can be done. The number of colors is not restricted in this definition. So we can just keep adding more colors as long as the lists are all of size at least K. But there are ways to check this, but you have to be a little bit smarter than just what the definition suggests. And then the edge choosability, or the edge list chromatic number, is the minimum K such that a graph is K edge choosable. And this is lower bounded by the or the edge chromatic number, because you can just make all the lists be 1, 2, 3 or something like that. Just make all the lists be the same colors, and since you have enough to color the graph according to the edge chromatic number, then you know that it's colorable. And since that's one of the possibilities you consider when you're asking if a graph is k-edge choosable, this is a lower bound. What I've shown in this example does not necessarily show that the edge choosability is equal to 3, because there could be some other edge list assignment that gives us a different result that isn't colorable. And so we would need to go through all those different list assignments. So the what's commonly called the list coloring conjecture, but I like to call the edge list coloring conjecture because it involves edges, is that for all graphs, the edge list chromatic number is equal to the edge chromatic number. And this is surprising because for vertex coloring, these two quantities can be arbitrarily different. The gap between them can be massive. But for edge coloring, these seem to be the same all the time. At least no one has found a counterexample yet to this conjecture. And there have been a few partial results over the years. So Galvin proved it for bipartite graphs, all bipartite graphs. Borden, Kostachka, and Woodall showed it for planar graphs that have a large maximum degree. Kahn in 2000 showed that it's true asymptotically that for graphs of large edge chromatic number that it's true. And then Woodall showed it for when the maximum average degree is bounded. This maximum average degree is kind of an overall measure of the density or sparseness of a graph, because you're looking at all the subgraphs and looking at their average degree and finding the maximum over all of those. And so if you had a graph that was like mostly sparse but had some really dense subgraphs, that this would be high. And so by giving an upper bound on the maximum average degree, Woodall kind of ensured that there was a sparseness all over the place, including in the subgraphs. And this is so the other half of the title is talking about the potential method. So just a brief overview of how the potential method works. So similar to the maximum average degree, we want to look at a particular quantity over all the subgraphs of a graph. In this case, the quantity is we have some constant times the number of vertices minus some constant times the number of edges. And so this is a similar measure of like how sparse or dense a graph is. But this one is linear as opposed to the average degree, which is like, the number of edges over the number of vertices. So it acts differently. But this is a linear measure and we want to minimize it over all of the subgraphs. And we call that the potential of a graph. And it is closely related to the maximum average degree because if we say the potential is positive, that's equivalent to giving a sharp upper bound on the maximum average degree where the bound depends on your constants. But the potential, like I mentioned before, is linear. So it changes in a very predictable way when you're adding and removing edges. And there have been some results where the potential method has been used. Most of them are relatively recent, but all of these used a positive bound on the potential. So essentially, saying the potential is strictly bigger than 0 gives you that maximum average degree bound, but saying that it is bigger than a positive number kind of gives you that the graph is like, you can remove a few edges and you're still bounded by the same maximum average degree. And that's how they were able to use the potential method, is like, hey, we can remove some of these edges and still we're within the bound. And that's how they were able to prove these results. But the main idea of what I worked on is, if we define the potential a certain way, then we can connect it really concretely to the discharging method that's often used in these coloring proofs. So a lot of these results are like, if I bound the maximum average degree by something, then I can color the graph in a certain way. And if we define the potential as being the minimum over all the subgraphs of A times the number of vertices minus 2 times the number of edges in that subgraph, then saying the potential is positive is equivalent to this maximum average degree bound of A. But in particular, if we look at discharging, this is just a sketch of how a discharging argument works. Like, you usually say you want a graph that is a minimal counterexample to the statement. So it has that maximum average degree bound, but it can't be colored. You show it can't have certain configurations. These are things that could be removed from the graph. Color the rest of the graph because it's a minimal counterexample, so the rest of it can be colored. Then when you put it back, you can extend the coloring to these things. So they can't, because of the fact that this is a minimal counterexample, it shouldn't be able to be colored. So these things can't be in there. But then you use this discharging method to show that they have to be in there. These reducible configurations are unavoidable. And this is the important part here, is what charges we're giving things. So we give each vertex a charge equal to its degree. And so the total charge, if you're adding up all the degrees of a graph, the total charge is 2 times the number of edges. Then we move those charges around, redistribute them according to local rules. Then what we want to get at the end of the argument is that the total charge at each vertex is at least A, are bound on the maximum average degree. But then that means the total charge after discharging is at least A times the number of vertices. Each vertex has at least A charge, so A times the number of vertices, which is what gives us our contradiction. It implies the maximum average degree is at least A, which shouldn't be the case. But what this means is that we get this nice little equation. So if defining the potential again like this, we get that the total final charge is this A times the number of vertices plus some extra charge. When we're talking about, some vertices may have more than A charge on them. But the initial charge is 2 times the number of edges. If we subtract one from the other, we should get 0 because we've just been redistributing the charge. But and so because of the way the potential is defined, we define the potential this way as A times the number of vertices minus 2 times the number of edges. We get that the potential is upper bounded by this negative quantity equal to the amount of extra charge we have in our discharging argument. And so this leads into what our particular results are going to be. So for edge list coloring, one of the reducible configurations is this thing called a K alternating subgraph. The definition is a lot to unpack, but the important thing here is this second condition. It looks really strange, but it's just a condition on the degree of the vertices in one of the two parts. This K alternating subgraph is a bipartite subgraph. And using this condition, this is where we'll find the extra charge that's left over when we're looking into our discharging argument. So this is the main result at the bottom here. The top part is just a definition of these quantities R and K or Q to figure out what the bound is going to be on our maximum average degree. And it's a little bit complex. Essentially, what's going on here is it's triangular numbers. So if we look at it's kind of like we're adding 1 and then we're adding 2 and then we're adding 3 sort of thing, and it's triangular numbers. Like at each triangular number we get a little bit more of a bound. But so this quantity A, which is our bound, is approximately equal to the square root of 2 times the max degree. And so that means that A minus the max degree is going to be negative. And so what the theorem is saying is that if we have a graph with this maximum degree bound and with a negative potential bound, then we get that the edge list coloring number is equal to the maximum degree. And
sorry to interrupt, Eric.
Yes.
It looks like we're a bit over time. If you can wrap up in the next 30 seconds, that'd be great.
Yeah, sure, I can. So this uses iterated discharging, and there's some extra charge left over, and that's where we get the bound. And so this is an improvement of Woodall's statement from 2010, because he was just saying that the potential is non-negative while this allows a negative potential on the graph, and there are graphs that have this negative potential. So thank you.
Thank you so much. Let's all thank the speaker. Are there any questions? We probably have time for 1 or 2.
Great talk.
I actually have a very quick question. So I've seen before other methods of measuring potential, like von Neumann graph entropy, and they usually involve the graph Laplacian to some degree. So I'm kind of curious, does your potential involve the graph Laplacian at all?
I think that's a coincidence of name. I'm not entirely sure why. I believe it was Kostachka and Yancey that first introduced this potential method. I'm not sure why they called it that, but it doesn't seem to have any sort of relation to the other kinds of graph potentials like that use the Laplacian, like you're saying. At least not that I know of. Maybe they knew of something and that's why they named it what they did, but not that I know of. So
Thank you.
I was gonna ask if you've like if you've looked into much applying these methods just to find the chromatic index, or because I think I've seen some like chromatic index type proofs that use something kind of similar to what you're describing. Yeah, were you able to, like, I don't know, come up with anything cool?
Personally no, but it is the case. The discharging method is well used in graph coloring problems, and looking at any of those proofs and seeing, like, trying to keep track of like what extra charge is there to be able to use this method instead, is certainly something that there's a lot of ground to cover there. But personally I haven't done anything along those lines. So
Okay.